The universe might not last as long as scientists once believed. Not slightly shorter, not by a small margin, but dramatically shorter. There is a real scientific possibility that everything could end without warning. No countdown, no signal, no final moment to prepare. One instant, everything exists. The next, everything is gone. Galaxies, stars, planets, space itself, even the atoms inside your body, all erased. For decades, scientists believed the universe would end in a slow and predictable way. A quiet fading over unimaginable time. A future so distant that it felt almost comforting. But new discoveries have started to challenge that idea in a serious way. Deep inside modern physics, there is a hidden instability, a fragile condition built into the fabric of reality itself. Most people have never heard of it. Even many science enthusiasts miss its full meaning, and yet it could decide the fate of everything. In this video, you will learn why some physicists now think the universe may be living on borrowed time. You will understand the strange concept that suggests reality itself is not as stable as it looks, and you will see how a single event smaller than an atom could instantly rewrite the laws of physics across the entire universe. This is not science fiction. This idea comes directly from the same theories that successfully explain particles, forces, and the structure of matter. The same physics that built modern technology is now pointing toward a deeply unsettling conclusion. The universe may not be permanent. For a long time, the dominant theory about the end of the universe was simple. Space is expanding. Galaxies are moving away from each other. Over time, stars burn out. Energy spreads thin. Everything cools down. Eventually, the universe becomes dark, cold, and empty. This scenario is often called heat death. It takes an almost impossible amount of time, trillions upon trillions of years. So long that human minds struggle to even grasp it. In that picture, nothing dramatic happens. There is no sudden collapse, no cosmic disaster, just a slow fading into silence. But modern physics has started to reveal something very different. At the deepest level, reality is not made of solid objects. It is made of fields, invisible structures that fill all of space. Every particle you know is simply a vibration in one of these fields. And one of those fields may not be stable. This is where things begin to change. Scientists have discovered that the state of our universe might not be the lowest possible state. In simple terms, reality might be sitting in a temporary condition, a kind of balance that looks stable but is not truly secure. This idea is called a false vacuum. It means the universe could suddenly shift into a more stable state. And if that happens, everything changes instantly. The laws of physics, the behavior of particles, the structure of matter, none of it survives the transition. This shift would not spread slowly. It would move at the speed of light, a growing bubble of new reality expanding in all directions. And here is the most unsettling part. There would be no warning. By the time any signal could reach you, it would already be over. This possibility is not just a random theory. It is based on precise measurements and mathematical models. It connects to real experiments, real data, real particles that scientists have already observed. That is why physicists take it seriously. That is also why it is so disturbing. To understand this better, we turn to one of the most respected voices in modern theoretical physics, Brian Greene. He has spent decades exploring the deepest questions about space, time, and reality. His work helps translate complex physics into ideas that reveal how strange the universe truly is. According to Greene, the universe might look stable on the surface, but at a deeper level, it could be balanced on a knife edge, a tiny change, a quantum fluctuation, something smaller than anything we can directly observe. That is all it would take. And this raises a powerful question. Is the universe truly stable, or is it only temporarily holding together? If the answer is the second, then everything we see is part of a temporary phase. a moment in a much larger and more uncertain reality. That includes every galaxy in the night sky, every star that has ever formed, every moment in human history. All of it exists inside a system that might not last. This video will take you step by step through the science behind this idea. You will see how physicists discovered this hidden instability. You will learn what the data actually says. And you will understand why the universe might not end in a slow fade, but in an instant. By the end, you will see reality in a completely different way. Because the biggest mystery is not just how the universe began. It is how stable it really is. Welcome to the channel. If you want to explore the deepest and most unsettling truths about the universe, make sure to subscribe and stay with us. For a long time, scientists believed the end of the universe would be slow, quiet, and almost uneventful. The idea is known as heat death. It begins with a simple observation. The universe is expanding. Galaxies are moving away from each other. This was first discovered nearly a century ago, and every new measurement has confirmed it. Space itself is stretching, but the real surprise came later. The expansion is not slowing down. It is speeding up. Something unknown is pushing the universe outward. Scientists call it dark energy. It makes up about 70% of the universe, yet no one knows exactly what it is. This invisible force acts against gravity. Instead of pulling things together, it drives them apart. Over billions of years, this effect becomes stronger and stronger. Galaxies drift farther away. Clusters break apart. Eventually, distant galaxies move so fast that their light can no longer reach us. They vanish from view, one by one. The night sky slowly empties. Then comes the next stage. Stars begin to die. They burn through their fuel and fade. New stars stop forming because the raw material becomes too spread out. The universe grows darker. After trillions of years, most stars are gone. Only faint remnants remain. White dwarfs, neutron stars, black holes. These objects linger for an incredibly long time, but even they are not permanent. Black holes slowly lose energy through a process called Hawking radiation. This is a subtle effect. It is so weak that it takes an unimaginable amount of time. A single black hole can last longer than all the current age of the universe multiplied by billions. But even they eventually disappear. At the end of this process, the universe reaches a state of maximum entropy. That means energy is spread out as evenly as possible. No structure, no motion, no useful energy left to power anything. Everything becomes cold. Everything becomes dark. Everything becomes still. This timeline stretches far beyond human understanding. Not billions of years, not trillions, much longer. Numbers so large, they lose meaning. And that is why this model felt safe. There is no sudden collapse, no violent destruction, no final moment where everything ends at once. Instead, the universe simply fades, slowly, quietly, almost peacefully. Even time itself loses significance in such a future. Without change, without motion, without events, time becomes meaningless. It is a universe that does not end with a bang, but with silence. For decades, this idea dominated cosmology. It was clean, predictable, supported by observation. It matched what scientists saw when they looked into deep space. But hidden inside the equations that describe reality, there was a detail that did not fit this calm picture. A detail that suggested the universe might not fade away at all. A detail that pointed towards something far more sudden. The calm picture of a slow and fading universe began to crack when physicists looked deeper into the nature of empty space. What seems like nothing is not truly empty. According to quantum field theory, every point in space is filled with invisible fields. These fields exist everywhere. Even in a perfect vacuum, they are still there. Particles are not tiny solid objects in this view. They are small vibrations in these fields. Electrons, quarks, photons, all of them are just patterns of energy moving through invisible structures. This changes how scientists think about emptiness. Empty space has energy. It has a state, and that state can vary. In simple terms, the vacuum of space can sit at different energy levels. Some are stable, some are not. A stable vacuum is like a ball resting at the bottom of a valley. It cannot roll any lower. It is at its true minimum. But there is another possibility. A ball can also sit in a shallow dip on the side of a hill. It looks stable. It stays in place. But it is not at the lowest point. With the right push, it can roll down into a deeper valley. This is the idea of a false vacuum. A false vacuum looks stable, but it is not the true ground state. It is a temporary condition, a delicate balance that can break. For a long time, this was just a mathematical idea, a strange feature in the equations. But things changed when scientists began to measure the properties of fundamental fields more precisely. One field became especially important, the field connected to the Higgs particle. The behavior of this field determines the structure of matter itself. It controls how particles get their mass. It shapes the stability of atoms. When physicists analyzed its properties, they found something unsettling. The current values suggest that our universe might not be sitting in the lowest possible energy state. Instead, it may be balanced in a higher energy state that only appears stable. This condition is called metastability. It means the universe can last for a very long time. It can appear completely stable, but deep down, it is not in its final form. There is a lower state waiting beneath it, and the transition to that lower state does not require a large event. It does not need a massive explosion or a cosmic collision. It can begin with a tiny fluctuation at the quantum level, something extremely small, something random, something impossible to predict. That tiny change could push the system out of its current state. Once that happens, the shift does not stay local. It spreads. A new region of space forms where the vacuum is in a lower energy state. Inside this region, the laws of physics are different. The values of fundamental constants can change. Forces behave in new ways. This region begins to expand, and it does not expand slowly. It moves outward at the fastest speed allowed in the universe, the speed of light. This is not a gradual transformation. It is a sudden rewrite of reality itself. Everything outside remains unchanged. Everything inside becomes something entirely different. And there is no barrier to stop it, no signal to warn of its arrival, no mechanism to reverse it. This is the discovery that changed how physicists think about the fate of the universe, because it means the end might not come from a slow fading. It could begin with a single transition. This leads to one of the most extreme ideas in modern physics, vacuum decay. In simple terms, it is the moment when the universe drops from a higher energy state to a lower one, like a ball finally slipping out of a shallow dip and falling into a deeper valley. But this is not just a small change. It is a complete rewrite of reality. When this transition begins, it does not happen everywhere at once. It starts at a single point, a tiny region where the vacuum shifts into a lower energy state. At that point, a bubble forms. This is not a bubble of gas or liquid. It is a region of space where the laws of physics are different. The values of fundamental constants change. The forces that hold matter together may no longer behave the same way. Inside this bubble, the universe as we know it cannot exist. Atoms may not form. Particles may not have the same masses. Chemistry could become impossible. Even the structure of space and time could be altered. And once this bubble appears, it does not stay small. It expands relentlessly. The edge of this bubble moves outward at the speed of light. Nothing can move faster than that. That means nothing can outrun it. No signal can escape it. No warning can travel ahead of it. By the time its presence is known, it has already arrived. This is one of the most unsettling parts of the idea. There is no countdown. There is no distant sign in the sky, no change in the stars, no shift in the background of space. Everything appears normal until the exact instant it is not. If such a bubble formed somewhere far away, it would travel across galaxies without being detected. It would pass through stars, planets, and empty space without slowing down. And when it reaches any location, the change is immediate. There is no time to react, no moment to observe it coming. From the perspective of anything inside, the transition is instant. One moment, the universe follows the familiar rules of physics. The next moment, those rules are gone. Matter does not break apart slowly. It does not burn or collapse in a dramatic explosion. It simply becomes incompatible with the new state of reality. It ceases to exist in its current form. Even light itself would behave differently inside this new vacuum. The basic structure of energy and motion could be altered in ways that current physics cannot fully predict. Some calculations suggest that even the concept of stable particles may disappear. This is why vacuum decay is considered the most dangerous possibility. Not because it is violent in a traditional sense, but because it is absolute. There is no survival scenario. No technology can stop it. No barrier can contain it. And no part of the universe is protected from it. What makes this even more unsettling is that the laws governing this process come directly from well-tested physics. The same equations that describe particles and forces also allow for this possibility. It is not an idea from speculation alone. It emerges naturally from the mathematics, and that raises a deeper question. If this process is possible, then everything depends on one critical detail: whether our universe is truly stable, or whether it is already on the edge. To understand how real this threat is, scientists turn to data. Not speculation, not guesswork, actual measurements from particle physics. At the center of this investigation is the Higgs field. This field fills all of space. It gives particles their mass. Without it, atoms would not form. Matter would not hold together. Everything depends on how this field behaves. For decades, the Higgs field was only a theory. Then in 2012, scientists at CERN detected a particle linked to it, the Higgs boson. This discovery confirmed that the field is real, but it also gave scientists something even more important: a number, the mass of the Higgs boson. This number may look small and technical, but it carries enormous meaning. It helps determine whether the Higgs field sits in a stable state or a temporary one. Physicists ran detailed calculations using this value. They combined it with other known constants, such as the mass of the top quark and the strength of fundamental forces. The results were surprising. The numbers do not clearly point to a stable universe. They do not clearly point to an unstable one either. Instead, they fall into a narrow and uncomfortable zone, a borderline region. In this region, the Higgs field is not in the lowest possible energy state, but it is also not unstable enough to collapse quickly. This is the definition of metastability. The universe appears stable on the surface. It behaves normally. It has lasted for billions of years without any sign of failure. But mathematically, it sits very close to a threshold. A small shift in the values could have made the universe completely stable. A slightly different shift could have made it collapse almost instantly after it formed. But reality sits right in between. This balance is so precise that it has puzzled physicists for years. Some describe it as a coincidence. Others see it as a clue that deeper laws are at work. There are even theories suggesting that many universes may exist, each with different values, and we happen to be in one that allows temporary stability. Another lesser-known detail makes this even more complex. These calculations assume that current physics remains valid at extremely high energies, but at those scales, unknown effects may appear. Gravity, quantum effects, and undiscovered particles could all change the outcome. That means the picture is incomplete. Some models suggest the universe could remain stable for a time far longer than its current age. Others suggest that rare quantum events could still trigger a transition at any moment, even if the probability is extremely low. This uncertainty is not small. It sits at the core of fundamental physics. scientists continue to refine their measurements. They build more precise detectors. They run more powerful simulations. Each improvement sharpens the numbers, but the overall picture remains the same. The universe is balanced in a delicate state, not clearly safe, not clearly doomed, right on the edge between stability and collapse, and that edge is defined by numbers that seem almost too precise to be accidental, which is why some physicists turn to a deeper interpretation of this fragile balance. This is where physicists like Brian Greene step in to explain what these results really mean. Greene often describes this idea in a way that removes the complex math but keeps the impact clear. He explains that the universe may look stable, but that appearance can be misleading. Beneath the surface, the structure of reality could be temporary, not unstable in an obvious way, not fragile in a way that can be seen or measured directly, but temporary in a deeper hidden sense. He compares it to a system that has settled into a calm state, even though a more stable state exists somewhere below. Everything functions normally. Nothing seems wrong. Yet the system is not in its final form. This is the core of vacuum instability. According to Greene, the unsettling part is not just that such a transition is possible. It is that the laws of physics allow it without contradiction. The same framework that explains atoms, forces, and particles also allows for the sudden rewriting of those rules. That creates a strange tension. Physics is meant to describe stability and predict behavior. But here it also predicts the possibility of a complete and unpredictable shift. Greene emphasizes that this does not mean the universe is about to end. The probabilities involved are extremely small. The timescales could be far beyond anything humans will ever experience. But the possibility itself changes how scientists think about reality. It removes the assumption that the universe is fixed and permanent. Instead, it introduces a new perspective. Reality may be more like a phase, a temporary arrangement of deeper structures that could change under the right conditions. Another point Greene highlights is how much remains unknown. The calculations that suggest metastability depend on current theories. These theories are powerful, but they are not complete. They do not fully include gravity at the quantum level. They do not explain all forces in a single unified way. There could be new physics waiting to be discovered. New particles, new fields, new principles. Any of these could stabilize the universe completely. Or they could reveal that the instability is even more severe than current models suggest. This uncertainty is not a weakness. It is a sign of how deep the problem goes. Greene often points out that every time physics has reached this level of precision, it has led to major breakthroughs. Moments where old ideas had to be replaced with new ones. This situation may be similar. The universe is giving clues, but the full picture is still hidden. And that leads to a more philosophical question. If reality itself might not be permanent, then everything built within it shares that condition. Every structure, every process, every moment, not in a dramatic or immediate sense, but in a fundamental one. The universe becomes less like a fixed stage and more like a temporary state, a state that has lasted for billions of years, a state that could, in principle, change. This idea does not affect daily life. It does not change how stars shine or how matter behaves right now, but it shifts the way existence is understood at the deepest level, because it suggests that stability is not guaranteed. It is something that may simply be, holding for now, and that perspective forces scientists to confront a final question that goes beyond equations. The first thing scientists are careful to say is simple. This is not something expected to happen anytime soon. The probability is extremely low, so low that it is often described as practically zero on human timescales. It is not a danger in the way people usually think about danger, but it is also not zero. And in physics, that difference matters. If vacuum decay is possible, even at an extremely small rate, then it becomes part of the structure of reality. It is not an external threat. It is built into the laws themselves. There is another unsettling detail. There is no known way to detect it in advance. A transition like this would not send warning signals. It would not create visible changes in distant space before it arrives. It would not show up in telescopes or measurements. The reason is simple. Any signal would move at the same speed as the change itself. That means nothing could reach us before the event happens. There is also no known way to prevent it. The process is not driven by external forces that can be controlled or blocked. It is driven by the fundamental state of the universe. The same laws that govern particles and fields also allow for this possibility. So even in principle, there is no technology that could interfere with it. This creates a strange contrast. On one side, everyday life feels stable. Stars follow predictable paths. Chemistry works the same way every day. Physics behaves consistently across all experiments. On the other side, deep theory suggests that this stability may not be absolute. It is conditional. It depends on the universe remaining in its current state. This difference between appearance and deeper structure is difficult to grasp. On the surface, everything looks permanent. But at the fundamental level, permanence is not guaranteed. Even the idea of time becomes more complex. Time feels continuous, steady because the laws of physics remain consistent. But if those laws were to shift, time itself would take on a different meaning inside the new state. This leads to a deeper realization. The universe may not be as stable as it appears, not in a visible way, not in a way that changes daily experience, but in a hidden structural way that exists beneath everything. Most people never encounter this idea in daily life. It does not affect technology or survival. It does not change how the world operates in practical terms. But in physics, it changes how reality is understood. It suggests that existence is not guaranteed by permanence, but by balance. A balance that holds under specific conditions. And those conditions may not be eternal. This raises questions that go beyond science alone, about how long anything can truly last, about whether stability is fundamental or temporary, and about what it means for something to exist in a universe where the rules themselves might not be fixed. These questions lead directly into a deeper and more uncomfortable possibility about the nature of existence itself. For most of modern science, the end of the universe was thought to be slow, a long, quiet fade into darkness, a future so distant that it felt almost harmless, a universe slowly running out of energy until nothing meaningful remained. But deeper physics tells a more complex story. It suggests that the end may not be slow at all. It could, in principle, be sudden, not from an explosion, not from an external force, but from a shift inside the very structure of reality itself, a change in the state of space, a transition in the fields that fill everything, a moment where the rules that define matter, energy, and time stop being what they are now. And that change would not arrive gradually. It would arrive at once. What makes this idea powerful is not that it is expected to happen. Scientists do not see signs of an approaching event. The probability is extremely small on any meaningful timescale, but it exists within the equations. That is the key point. The same mathematics that explains atoms, light, and galaxies also allows for a universe that is not completely stable. A universe that holds together, not because it must, but because it has not yet shifted into something deeper. This creates a tension at the heart of modern physics. On one side is precision, measurements, predictions, technology that depends on consistent laws of nature. On the other side is uncertainty at the deepest level, a reminder that these laws may describe a temporary arrangement, not a final one. Both are true at the same time. That is what makes the idea so difficult to fully accept. It does not change daily life. The stars will still shine. Physics will still work. The world will continue in its predictable way. But But underneath that stability, there is a possibility that reality is not permanent, not in a way that can be seen, not in a way that can be measured directly, but in a way that exists in the structure of the universe itself. This leads to a final thought. Everything observed, everything built, everything experienced exists inside a system that may not be the final version of reality. A system that could, in principle, change without warning. And if that is true, then the universe is not just expanding through space. It is moving through possibilities, some stable, some temporary, some still unknown. The question is not only how the universe will end, it is whether the state we call reality is permanent at all.